today's lesson, I will apologize ahead of time, is probably the most technical lesson we're going to do. The most, if you want to call it, scientific lesson. And I apologize for that, but I think it's necessary, so just stay with me on it. It's not that difficult to understand, but it is probably the most technical one that we do. And it's going to be we're going to be looking at the concept of entropy. Now, you won't find entropy in the Bible. For that matter, I don't think the word gravity occurs in the Bible. Neither does electromagnetism occur in the Bible. These are not biblical concepts, but it's just the way that physicists have looked at our world and have decided how the universe seems to work. And entropy is one of the 3 laws. Some say 4 laws of thermodynamics. There's actually a 0 law, which no one ever talks about. The first law of thermodynamics has to do with the conservation of energy. Entropy has to do with orderedness and other things, information and so forth. We're going to look at it in detail. And the third law of thermodynamics has to do with the idea that we can never achieve 0 temperature, or absolute 0 temperature. You can't achieve it. We're not going to be talking about that law. We're not even going to be talking about the first law. We're going to be talking about the second law primarily. And the reason we want to talk about the second law is when you're reading your books on creationism, especially if you remember that book early on, the 50 scientists, the 360 days, some of you have that book. You'll see several scientists in there talk about how life violates the second law of thermodynamics, or entropy. And I've read that even since I was a much younger man in college and in high school. And you need to understand what that means, because someone's going to argue that life does not violate the second law of thermodynamics. In fact, if you remember in that debate earlier on this year that Bill Nye had with Ken Ham, Ken Ham brought that up, and Bill Nye just kind of sloughed it off, saying, well, the sun is responsible for life and it doesn't violate the second law of thermodynamics. So you're going to see those arguments and you're going to hear those arguments. So I think it's important to know what scientists are talking about, because I have one concept of entropy, but then the more I studied and the more I've looked at this information, my concept was not 100% correct on what the word entropy is. But in short, entropy is the second law of thermodynamics. And again, on the surface, creationists propose that it violates the second law. Well, what is the kind of definition of entropy that you remember? We mentioned it here a few weeks ago on what the word entropy means. Do you recall what that definition was? You said it a few weeks ago. Disorderedness. And that's the definition, and that's an accurate definition. That's what entropy is. And so when you look at the word disorderedness and you look at life seems to be complex and very ordered, right? And so on the surface it looks like life violates that second law. Problem is, entropy is more complex than just disorderedness. And so the physicist will tell you it encompasses more than just disorderedness, although that is an accurate definition of entropy. It involves disorderedness. So evolutionists would say that life does not deny that. So what we want to look at is, first of all, is entropy a non-mutable law of the universe? What is it? And is it non-variable? Does it always occur? And then secondly, how would the naturalist, in this case physicist, try to prove that life doesn't violate that second law? And we'll see how in fact it really does. The beginning of life does. So let's look at entropy. So the second law of entropy is one of the second laws of thermodynamics. So it has to do with thermo, meaning heat, the laws of heat and heat changes and that sort of thing. And it has to do with time, energy, and disorderedness. And it seems to be immutable and has even been referred to as a meta-law. It's a law that supersedes a lot of other laws. And different laws of physics are based upon the concept of entropy. Dr. Benjamin Schumacher would even say that entropy involves information. And when entropy increases, information in the system also increases. Now, he's looking at information from the concept of Shannon information. Don't want to go in detail what that is, but Shannon information is not necessarily information as you and I see information, and is not specified information. And we looked at that several classes ago. But that's one way of looking at entropy. It involves time, it involves energy, it involves disorderedness. And again, it is a meta law. Well, how did we come up with this idea? If it's not in the Bible, and the ancients didn't talk about entropy way back in the days of Plato and Aristotle and people like that, where did the concept come from? It seemed to have been first formulated by a fellow by the name of Sadi Carnot. Carnot was a French engineer, and he was looking at the steam engine. And Carnot was trying to develop the most efficient steam engine he possibly could. And so he came up, he didn't call it entropy at that time, but he came up with a concept that this steam engine, you could never get just an efficient steam engine that went from zero entropy back to zero entropy. Entropy was always going to be lost. There was also always going to be a loss of heat when you developed a steam engine. There would never be a steam engine that could be run without the loss of heat. So Carnot was the first to really describe the concept of entropy, although he did not name it. A few years later, we have German physicist Rudolf Clausius. And Clausius expanded Carnot's original idea, and he came to realize that Carnot was not really he was really talking about a basic physical law of the universe. He came to understand that. And Clausius discovered that heat always flows in one direction. Now that may seem very simplistic to you, but that's one concept of entropy, the idea that heat always flows in one direction. And you know this as well. If you pour hot water into cold water, what happens? The cold water gets warmer, right? That's entropy. Believe it or not, that is one concept of entropy. And this was a basic phenomenon that men have known for millennium, but it's still, that is the basic concept of entropy. So if you put, in this case, you got, I guess, on the A, you got hot water, and C, you got cold water, and you got a conduit that goes from one to the other. But just think of the idea of a glass of hot water and a glass of cold water and pouring them together. And the heat's always going to cause the cold water to become warmer. Though you could say, well, the cold water makes the hot water become cooler. That's one way of looking at it, but that's what happens is the heat flows in one direction and the cold water becomes warmer. And it's this gradient, this going to equilibrium, which is entropy. That's one way of looking at entropy. It's going to a thermal equilibrium as a result. Now, does the world have to work like that? Does it absolutely have to work that way? It doesn't have to work that way, but it sure does. You don't pour cold and hot water and you have in your glass, and then you'll have one side of cold and one side of hot, would you? You wouldn't have that. You would have a thermal equilibrium, and that is entropy. So Clausius invented the word entropy to explain exactly what was happening. And entropy was the change of heat divided by the temperature, always flows in a positive direction, and entropy is going from more order to disorder as a result. And when this is accomplished, work is done. Entropy is the reason your steam engine works. It's the reason your car engine works. It's because of this concept of entropy. And in fact, one way of looking at entropy is that entropy is something that we would call fuel. Okay? If you had a stick of coal, that is at low entropy. When you ignite that stick of coal and it starts burning, you're going from a low entropy system to a high entropy system, or gasoline, or wood, or whatever you want to call it. That is the concept of entropy. Another way of looking at entropy is to contemplate that entropy increases because of what physicists call the arrow of time. Now, this is also a fundamental concept that you would say, well, it's just painfully obvious. Time goes in one direction, but does it have to? I mean, it does, but does it absolutely have to? Well, in our universe, it has to. It's impossible for entropy to go or for time to go in a backward direction. You can foresee the future, okay? You can foresee it, but time you can't do anything, the past you can't do anything about. And that's fundamental in our universe, and it's part of why entropy increases in our universe, or seems to. In 1870, Ludwig Boltzmann tried to give a mathematical equation for entropy. And he defined entropy as being thermal energy, the random motion of atoms. His insight was that entropy is simply a way of counting the number of arrangements in atoms in a certain system. What is heat? Do you know what heat is? Anybody want to venture to tell me what heat actually is? When something gets hot.
Moving quickly.
Correct, exactly. atoms or molecules beginning to move more quickly. That's heat. When they don't move as quick, you've got cold, okay? So that's saying, you know, for 1870, that was something profound. Now it doesn't seem so profound, but back then it was. And Ludwig Boltzmann was responsible for that idea. So he looked at heat, and he looked at the arrangement of atoms. So when you go from a cold system to a hot system, what's happening to entropy? It's increasing. That's what's happening. And he put a mathematical equation to that. Boltzmann's entropy was the number of possible microstates a given entity can be at. And he basically said it's real obvious. The reason entropy increases, according to Boltzmann, was simply there are more ways to go to high entropy than to low entropy. You know, it wasn't a real dilemma to him. You have to go from high to from low to high. And so if you've got a container of atoms and you increase the heat of that atoms, you're increasing the movement of those atoms, and you have more microstates, if you will. And so the equation for that is entropy equals Boltzmann's constant times the logarithm of the number of ways we can arrange things. So sometimes what gets confusing is entropy and complexity, because we confuse the two together, and you can't confuse the two together. Something can be very complex but still be at low entropy. We'll go into more detail to that in a minute, and that's one of the ways they circumvent the idea of life a little bit. But it's in essence true. You can have something that's complex that's still at low entropy. One way of thinking about it. A few months ago, as y'all know, we took a little trip to France, and you go see the Eiffel Tower, and when you get out of the Eiffel Tower, you see these people selling these miniature Eiffel Towers, okay? And so you got the little bitty Eiffel Tower, and you got the real big Eiffel Tower. Well, there's only so many microstates of that mini Eiffel Tower. That would be a low entropy. The big Eiffel Tower has a lot more ways, a lot more microstates to explain it. That would be an example of something now that is at high entropy. James Clerk Maxwell, you know who Maxwell was? Maxwell is the kind of the father of electromagnetism, and he developed the equations for electromagnetism, a brilliant man. And still we use those equations today, and who knows what would have happened had we not had someone like James Clerk Maxwell come along. Maxwell looked at this idea of entropy, and that entropy was always increasing. And Maxwell tried to devise an experiment where entropy does not necessarily have to increase. And so he came up with the idea of Maxwell's demon. And that's what we got a picture here. Now this is a thought experiment. This is not an actual experiment. Obviously he didn't put a little demon there. We don't have demons like this to do. But the kind of the classic example of entropy is where you have a box like this with a divider down the middle. And let's say instead of having all the atoms in both boxes, we put all the atoms in the left-hand box. Then we make a hole in that box. What would you expect to happen? Or let's say we lifted the divider. Forget the hole for right now, but we lifted the divider in the box. What would you expect to happen with those atoms? Let's say it's a gas. Make it kind of simple. It's some sort of gas, helium or hydrogen or some other gas. We've got them in a box with a division. We lift that division up. What's going to happen? It's going to go to the other side, right? Those atoms are not going to stay congregated on that left-hand side. That's entropy. That's what entropy is. That's how your piston engines work. Now you can change entropy, but you've got to do work to get entropy back to where it was. And you, as a result of doing that work, you've now increased the entropy. So Maxwell came up with this idea of putting someone in there, and let's see, now instead of taking the divider out, we got a little hole in the divider. And so we expect from the random motion of those atoms that eventually those atoms are going to go through that hole and fill up that other side. That's what we would expect. That's what happens in the natural world, right? So he had this idea of a demon there that would block those atoms from going over, okay? He would sit there, and as they came to that hole, he would block them. It's funny how physicists work. They come up with all these thought experiments. Thought experiments are good experiments. The theory of relativity is based on thought experiments. Einstein didn't do any hard physics as far as experiments. His was all thought experiments. But in this case, Maxwell came up with an idea that you could keep entropy from going from one side to the other if you had something that would block those atoms from going over there. The problem is you don't have anything to block those things from going over there. And if you did have something that was blocking those atoms from going the other side, you've added information to the system now. So his thought experiment really didn't work. But he did come up, his insight was that he did come up with an equation in which that could possibly be done. And it's possible that entropy doesn't have to go from low to high. It's possible. But the possibility is a statistical impossibility because the chances of that happening are astronomically low. We're talking about extremely low. Now, this is something I find curious. When physics finds something that is an impossible, something that's statistically impossible, there's three ways of defining impossible. There's the absolute impossible. If you look at mathematics, 2 plus 2 is 4. It's got to be 4. You can't do anything but 4. That is an absolute impossibility for 2 plus 2 to equal 5, right? That's an impossibility. And if you look at the geometry and the work with triangles and Euclid and all that, those are absolute impossibilities. There are possibilities that are derived against acceptable assumptions in the physical world. Turns out entropy is a statistical impossibility. But if you recall in this class, we've solved the possibility of life occurring by chance. Was that not a statistical impossibility as well? So physicists will recognize statistical impossibilities. It's not totally impossible for entropy to go from 0 to higher, but it's statistically impossible. We recognize that in life too. I just throw that to the side because they understand when things are so astronomically unlikely, they become a statistical impossibility, and that's what you have with entropy. Another way of looking at entropy, and I was going to bring a little, you know these little plastic candy eggs? Let's say you put some gas in there once again, and you open that egg up. What would you expect to happen? That gas to stay in that nice configuration? Of course not. It's going to spread out throughout the room. That's the concept of entropy. But also, let's take an egg that has not been broken, and you drop it on the floor. When that egg is dropped on the floor, it cracks, it opens. You've gone from low entropy to high entropy. That's what entropy is. So I hope that clarifies at least a little bit the concept of entropy. If you have any questions on that. But that's the way our universe works. It's a fundamental fact of the universe, is we go from low entropy to high entropy. That's just the way the universe works. So, for a physicist, the universe began at a very, very low entropy state, and then you had the Big Bang. Okay, that's according to the physicist. Since the Big Bang, entropy has been increasing in the universe, and it will until the universe reaches equilibrium. Again, think about that glass with cold water and hot water. You pour them together and you got thermal equilibrium. Well, eventually, according to the physicist, the universe will reach thermal equilibrium, and that time we're all gone. We're dead. That's heat death or thermal death of the universe when that occurs. But it all began as a very, 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 very infinitesimally low amount of entropy. Not energy, entropy. So the obvious question, why was entropy low at the beginning of the universe? And why was there a Big Bang to begin with? Well, those why questions, they don't know. That's just their theory. That's just what they state. But you can't get past that. They have no concept or no idea of why entropy had to be low at the beginning of the universe, or that it was low at the beginning of the universe, but that's the concept. And I guess in some ways they're actually correct. Before there was a universe, there was nothing. It was low entropy, and then God said, let there be light, and there was a lot of entropy. We went from low to high real quick, didn't we? So, beyond that, physicists must answer the question as to why life has occurred. What is the purpose of life? And why was life changed from less complex to more complex? Now, this is something that even evolutionists cannot explain. Why does evolution have to go from less complex to more complex? Do you have any idea? Well, it don't. There's no physical law that says that life has to go, if you believe in evolution, which we obviously in this class do not, but if you believe in evolution, there's no physical law that says that you have to go from less complex to more complex. But it does. So physicists, the physicists are curious scientists, if you will. They're real hard, fast scientists. They're looking for physical explanations of the universe. That's what they're looking for. So they have to come up with some idea, you would think at least, to how to explain why life must go from the least complex to the more complex. Wouldn't a bacteria just be happy being a bacteria? Wouldn't it? Or a virus being a virus? But there has to, the physical laws just do not demand it. It's not something that's demanded by any physical law no one can identify, anybody can identify. And here's their answer. Their answer is entropy decreases in a small system, that's life. But it does so because it's increasing in a much greater, wider scale. That's the answer. It temporarily decreases in a small system, that's life, that's you and me, once again. But it does so because entropy is increasing on a larger scale. Now, I see people shaking their heads. I agree with you, but that's their explanation, and we will look at that in detail. So in other words, they admit, at least this is my point of view, okay? This is me talking here. From my point of view, they admit that life violates the second law of thermodynamics. And even though there's no experiment scientifically that any other system in the universe does, that I'm aware of, no scientific experiments have ever shown that entropy doesn't increase. But they will admit, and they will say in a non-closed system, and they use that word to explain why it can occur. So temporarily, the law is violated, but it's at the expense of increasing entropy throughout the universe. That's their explanation. So once again, physicists ask us not to confuse complexity or simplicity with low entropy and high entropy. Low complexity and high complexity do not equal low entropy and high entropy. They're different things. Complexity is not the same as entropy. High complexity does not equal high entropy. In the 1960s, one of our few Soviet scientists that we've looked at in this class, Andrei Kolmogorov, defined complexity as the length of the shortest description that can capture everything relevant about that thing. So what that bottom line means is if it takes you longer to describe it, that means it has more complexity. Okay, these are profound statements, aren't they? No, we knew that really already, kind of. But scientists have to put this in action. So in the 1960s, Kolmogorov came up with this idea. If it takes you long to explain something, that means it must be more complex. So physicist Sean Carroll, the California Institute of Technology, Caltech, explains that complexity can arrive when entropy is in between low and high states. So what he's trying to explain here is that life is in between. And so we're complex, okay? Life is complex. And so arriving from a low complex, high complex, there is an in-between state, and then it becomes less complex. What's the example that they show in physics? Sean Carroll does, at least. Let's say you got a kind of the same concept of a cold to hot coffee. You got a water. We're going to use coffee in this case. And we're going to get black coffee, and we're going to use a glass, a cup that you can see through to make it easy. You're going to pour cream into the coffee. White cream into black coffee. What happens when you do that? Well, it'll cool the coffee up a little bit, but that's not what we're looking for here in this case. What we're looking for is the color of the coffee. And you'll take that coffee and you'll make it go from black to what? Brown. But what happens in between? It's not brown instantly, is it? It's kind of a creamy color, and you see the swirling of the cream in the coffee, and it looks very complex. It's a complex system for a short period of time. And then it turns to total brown, and now it's pretty simplistic. But you've gone from low entropy to high entropy at the very end. That's their explanation for why you can have a complex system temporarily and still have low entropy going to high entropy. And so he says the simple fact is that entropy is increasing is what makes life possible. This is a physicist explanation. So You and I are here to increase entropy. So let's define life. We've looked at life in quite a bit of detail here. And we know, for example, that life is made up of DNA and RNA. You know, and one of the features of life is that it replicates itself, you know, or you don't have life. If peas can't replicate peas, if bacteria can't replicate bacteria, if men can't replicate men, then you don't have life. But life would cease. But that's not really a satisfactory definition for a physicist, okay? And so you got a fellow by the name of Erwin Schrodinger. Anybody heard of Schrodinger in this class? Right, Schrodinger's equations. He's involved in equations. You ever heard of you may have, since you know of Schrodinger, ever heard of the cat experiment, thought experiment with Schrodinger? I mean, these are thought experiments, but Schrodinger was the pioneer, one of the pioneers of quantum physics. Brilliant man. And his equations, Schrodinger's equations are part of the quantum world now, and they're still used in the quantum world now. Quantum physics we'll look at a little bit when we get into creation and so forth, but you come up with some absurd endpoints when you look at quantum physics. And what scientists have sometimes done, if they've taken the science of quantum physics and then tried to apply it using thought experiments to the philosophical. So when Schrodinger had this idea that there's a cat in a box and you got cyanide pellet in the box, you open the cyanide pellet in the box, but the cat won't actually die until you open the box and you see it dead. That's his thought experiment, but that's another topic. But he did try to define life. So what is life to a physicist? Well, here's what Schrodinger said. Schrodinger said it's something that goes on doing something longer than you would expect it to. That's life. And it's a pretty profound statement because it's actually true. Physical reactions have an endpoint and they stop. But life goes on. And so let's go back to our previous example of cream in a cup of coffee. Let's say instead of putting cream in a cup of coffee, we put a goldfish into a bowl of water. Now, we don't expect that goldfish to reach thermal equilibrium immediately, do we? That's life. It goes on longer than you would expect it to. When you put cream in that coffee, it's gonna equilibrate very, very quickly. But life doesn't do that. That goldfish will go on for days, probably, unless you don't feed it. Then it's eventually going to die. But it's not going to reach thermal equilibrium. And that's what life was to Schrodinger and to physicists. So in the physical nature, this is not what typically happens in the universe. It's just that simple. Life is something that goes on a lot longer than you would expect it to. So how does life defy the second law of thermodynamics? Some have stated, and I've mentioned this earlier today, that the sun is responsible for life on the earth, and there's a way in which it certainly is, and hence it's responsible for this apparent contradiction in the second law of thermodynamics. Bill Nye mentioned this in his debate with Ken Ham. This isn't actually accurate, and you think about it, it wouldn't be accurate. It can't be just the sun. Why not? It's not the sun that causes life, but it's the change in entropy, believe it or not. Because if the sun wasn't rotating and you had the sun beating down on the earth, would life be able to exist? No, we'd be burned to death. So this earth has to rotate. This goes back a little bit to that class of the video you guys saw last week. There's reasons that life occurs on earth. And clearly one of the reasons is the tilt of the axis and the fact that it rotates. And it's going from hot to cold. It's going from light to dark. That is responsible for the change in entropy and hence allows life, not causes life in my opinion at all, but it allows life to exist on earth. So the actuality is the earth gives back more energy. It says as much there, but it says more energy as we get through the sun through the radiation that occurs at night through infrared light. For every 1 photon from the sun, the earth gives back 20 photons at night. We increase entropy by a factor of 20. And the global nature of this argument is that life on earth does not violate the second law of thermodynamics because of that. But let's look further. So one quality of life we've already mentioned is that it has to replicate itself. So some physicists believe in a metabolism-first theory regarding the origins of life, not what we've looked at in the past, which was the RNA world. I think they look at this because they realize that that doesn't make sense. How does RNA begin in the first place? So they argue complex chemical reactions take advantage of the low entropy environment of the Earth. And this is sort of the hardware before the software approach. You know, that's the way they look at it. You have the hardware before the software. The hardware is no good without software. I'm not a computer genius, but that's the way I understand it at least. Your hardware won't do you any good if you don't have a software. And this is their approach. But there's a problem. And it goes back again to our ancient problem of information that we've already looked at in this class. If you have something going from an original situation of low entropy to high entropy, and it requires a chain reaction that is very difficult to get started. They admit that. Just almost impossible to get started. And this argument is that reactions occurred in very specific geologic formations. Well, what do you see with the problem there? I've already hinted at it. And that is specific geologic formations imply design and would require information. So they still can't get around the information problem. Low entropy to high entropy doesn't explain how life got here. You still have to have information. So physicists then postulate that life started in order to increase the entropy of the primitive life's atmosphere. Why? Why does entropy have to be increased? Why would the Earth want entropy increased? It's almost like you're giving personality to innate things. And I've stated here, it's circular. Why would Earth want to increase it, and who would direct it to begin with? The bottom line is, and this is really, you know, when I researched some of this stuff and look at Sean Carroll and Schumacher and some of these really brilliant men and physicists, and they start venturing into the realm of creation and into the realm of life, they haven't got a clue. The bottom line is physicists know how difficult it is to explain the origins of life. They don't really want to, most of them don't want to get involved in that. They just want to stay away from it because they realize how difficult it is. And you understand these are people that are dealing with relativity and quantum physics. They're brilliant men. You know, some ideas that you and I would have an extreme hard time grasping. And yet they don't want to get involved in the idea of how life began. And they know that. But yet some of them still try. Our present universe from a physical standpoint simply does not give the answers to physicists on how life began. In order to explain it, they have to, and this comes from Sean Carroll actually, Caltech. In order to explain it, they invoke the many worlds hypothesis, or sometimes referred to as the multiverse hypothesis. Have you heard of that hypothesis? That is that there's an infinite number of universes. That's their hypothesis. And with an infinite number of universes, you can produce life eventually. And in other words, sooner or later, universes had to acquire life, even if we can't explain it in our universe. If you've got infinite number of universes, it could be explained. And I think this is parallel to the evolutionist argument, don't you? The evolutionists say that with enough time, evolution can occur. The physicists say with enough universes, life could occur. That some and this is from Stephen Meyer, that some scientists dignify the many world hypothesis with serious discussion may speak more to the unimpeachable commitment to naturalistic philosophy than any compelling merit for the idea of itself. Can you test the multiverse hypothesis? You can't test that. It's philosophical. And the fact that they even have to come up with it mean they're committed to naturalism. And I agree with Stephen Meyer. The proof of entropy is all around us. We understand that cars rust, bananas spoil, we die, the death of a plant once it's dead, and us included, there's no information left in there. That's the increase of entropy. And death is the ultimate. Andrew McIntosh, PhD in mathematics, University of Wales, says what is paramount in the discussion is the information, that is the setting of the rules, the language code, etc., has been there from the beginning. The physical laws of the universe do not explain this. You can't explain why entropy increases. It was there from the beginning. Just like all the other physical laws, electromagnetism and so forth. Chemicals do not define the message they are carrying. Information cannot be defined simply by physics or chemistry. We've looked at this before. They're the carrier of the information. The DNA, the codons in the DNA carry the information. They're not the information. They carry the information. Someone had to put that information in there. Kerr Thompson, geophysicist, brilliant man, clearly and correctly states, only a purposive machine could temporarily obviate the second law's demands. The idea that the second law can be confined to a closed system is a piece of confusion on the part of the proponent of such concept. They just have to throw that in there, this idea of closed system. Dr. Thompson goes on to say the second law tells us clearly that life could never get started by the activities of matter and energy unaided by outside intelligence. And I'd say amen to that. Our original question, does life violate the second law of thermodynamics? I know this is lengthy, but from a physicist's standpoint, this is what has to happen. It requires them to evoke theories that they cannot prove. When one has to use multi-universe theories or defer to explaining life's apparent contradiction to the second law as being the result of a non-closed system, or only temporary decreasing entropy for the wider purpose of increasing it, or even the biggest cop-out of all, merely stating that life exists to increase the overall entropy of the universe, are simply poor arguments and defy the obvious, that being life is truly the result of a grand design from a higher intelligence. I know that's a long sentence, but it conveys everything I wanted it to convey in that sentence. They're copping out. They don't have really a physical explanation for life, so they have to come up, we have to come up with multiverse universes. Now, is it possible you could have multiverse universes? According to the physicists, it's possible, but we know that that's a cop-out. John Cimbalos, PhD from Caltech, interesting. Here's a guy from Caltech, and Sean Carroll's a guy from Caltech. They both have opposing views. Only someone or something not bound by the second law of thermodynamics could be responsible for the universe. God, in other words. He's not bound by these laws, is he? He's not bound by entropy. He's not bound by the first law of thermodynamics, conservation of energy. He's not bound by it. Only the creator of the second law of thermodynamics could violate it and create energy in a state of availability in the first place. Cimbalos concludes the universe has had a beginning, and that beginning had to have been caused by someone or something operating outside the known laws of thermodynamics, and hence, yes, life does violate the second law of thermodynamics, but someone put it there to allow it to. And you can try to explain it away all you want, but bottom line is, because we're here, we have violated that second law, and we're here as a result of that.